Hello everyone. In this set of videos we're going to be talking about VXLAN multi-site and specifically setting up this fabric here in front of us. This is the same fabric as the blog post that I did last year on VXLAN multi-site. There are going to be some additional configuration additions and changes just in line with best practices from that blog post, so they're going to be included in here as well. So as we can see, we've got two data centers, DC1, DC2. They've each got their own little spine leaf architecture with two spines and two leaves, and then they've got these core switches up at the top which connect the data centers. The spines and the core switches are fully meshed, as are the spine and leaf, as per the spine and leaf architecture. We've also got a couple of firewalls down here which aren't switched on at the moment, and therefore later down the line when we get access outside the fabric, so they'll come in a future video. We've also got then the end hosts down here in the different VLANs to allow communication. So in this video we're going to configure the underlay, the overlay, including the multi-site configuration in order to get the machines communicating with each other on layer 2, and then in a subsequent video there'll be the tenant configuration on top of that for the layer 3 communication, and then allowing access outside of the fabric. So first things first, let me show what we've got. So show version. These are 9300 V chassis. I'd previously used 95s, but they run quite heavy on resources, and it's a bit lighter running the 93s, and they can do all the same configuration. We are running 10.3.5, which is a main initial release, which is Cisco's latest recommended version at the time of recording. So fingers crossed, everything should work on that version. We shouldn't have any issues. So we've also got the PCs here, so we've got access to these, so we can do some connectivity testing between them once the fabric is set up to prove connectivity is working and that we can reach the different areas of the network. So cool. Right, let's get on with the configuration then of the switches. So the first thing we need to do is enable a load of features. So I will do it on this one switch and then copy it to the rest of them. So we'll enable OSPF for our underlay, enable BGP for our overlay, PIM. We also want fabric forwarding, interface VLAN, VN segment based, and finally NVE overlay. Just grab those commands and then get them everywhere else as well. There we go. And I'll use secure CRT to my advantage and whack that everywhere. So that should have gone on all switches. It looks like it has. Cool. So next thing to do is configure a loopback 0. So we've got these are the loopback 0 addresses. There will be later additional loopbacks on pretty much all the switches, because Cisco recommend that the router ID and the VTEP address are on separate loopbacks. So for the cores and the leaves, which are all essentially VXLAN VTEP switches, will have an additional loopback. The cores will have another loopback for the intersite connectivity, and then the spines will have another loopback anyway for the PIM root reflector configuration. So let's get loopback 0 configured first. So interface loopback 0, we'll now shut that globally, and then we will IP address. Just run around and whack these everywhere. So 1, this will be 2, 3. Nope, that's moved. 4, and then spines 5. 7, 8, 9, 10, 11, and last but not least, 12. Cool. So now globally we can just enable OSPF, so router OSPF, and we'll call it Underlay, and just for good measure we'll log adjacency changes. We'll also enable that under the loopback 0. So IP router OSPF underlay area, and we're in the backbone area, so do that on there. So that's the loopbacks configured. So now what we need to do is configure what I consider the fabric interfaces, which are the interfaces between the leaves and the spines. As we can see on all the spines, pointing down to the leaves, it's all ETH1, 1 and ETH1, 2. So thankfully we can use an interface range command for that. So we'll come onto the spines in DC1, int ETH1, 1 to 2. We'll make it not a switch port. We'll set the MTU to 92.1.6 for jumbo frames. We'll set medium, PIP, IP on numbered, loopback 0, IP OSPF underlay area 0, IP router OSPF, and IP OSPF network point to point, and we'll now shut that as well. So run int ETH1, just grab that configuration, and what we'll do is on this spine we will 1 to 2 again, and to be fair we can do that on the leaves as well, because if we look at the leaves, 1 and 1 and 1 2 are the interfaces pointing up to the spines, and the configuration is exactly the same on them. So what I'll do is I'll just add this to here, int ETH1 1 to 2, whack that on there, and then these are the spines in data center 2 on the exact same configuration, putting on them. So look what that should mean for us is if we do show IP OSPF neighbor, we've got 4 neighbors, so 6 we see twice, and then 9 and 10. So that should, one of these 6s should time out. But yeah, essentially we've now got a full mesh within each data center of OSPF peerings. So if we come on here and do the same thing, we can see 2 on there, 2 on there, and 2 on there. So that's what we expect. And from a connectivity perspective, so we're in DC2 spine 1, we should be able to ping DC2 leaf 2, which is .12. So from here we should be able to ping 10.0.0.12, and we can, which is a good sign for connectivity. So now looking at the configuration on the interfaces between the spines and the cores, they won't be using IP unnumbered. We'll have to enable actual what I would call a link net between them, so just like a /30 between the two switches, and then the same on the DCI links, the data center interconnects. So let's get configuring those. So from a we'll go in sequential order, so we'll do DC1 and then DC2, and we'll configure each link at a time so we don't get confused. So right, ETH1/3. So for the minute, what we'll do is we'll configure the interface, we'll configure the IPs now, and then afterwards we'll configure the actual other configuration for the interfaces like the MTU, the OSPF stuff. So for now we'll just get the IPs on there. So we'll have to no switch port them. IP address 10.1.1.1/30. So that'll put us on DC1 spine 1 ETH1/3. So fortunately some of them are the same interface name, but it starts to not be that when you get some of these other ones. So int ETH1/3, we'll do 2 no switch ports. Then we'll do, let's just have a look at show CDP neighbors. Cool, so let's configure this interface, and we will go with 5, no switch port again, 5, and that maps to spine 2 ETH1/3. No switch port 6. So that's both links done on this core switch. So show CDP neighbors. So again we are 3 and 4. So IP address. Again no switch port. So this will be 9. And where does that map to? That maps to spine 1 ETH1/14. Sorry, ETH1/4. No switch ports. 10. And then int ETH1/4. Switch ports. So 10. 13. That goes to spine 2 ETH1/4. No switch ports. And 14. So now what we'll do is 3 to 4. We will enable the other configuration. So MTU 92.16 IP OSPF network points IP router OSPF underlay maybe 0. We'll do medium P2P, and we'll also no shot them. Cool, so we'll grab that. Whip the IP out of there. Have the same configuration pretty much. It's 3, 4, 3, 4, 3, 4. So we can do that across the board. Perfect. And then let's jump into DC2 and start doing the same thing. So show CDP neighbors. So let's 1/3 IP address no switch port, IP address 10.2.2.1/30. May as well, while we're on here, /4.5. I'll get it one day. So 1/3 goes to 1/3 on spine 1. That will be IP address 10.2.2.2/30. And then from DC1, Core 2, we also configured ETH1/4, which goes to I guess that's, yeah, okay, one sec, I've just got the wrong name. That was confusing for a second. So this goes to 1/4. That'll be 6. So that's that switch done. Then on here, show CDP neighbors, call int ETH1/3, no switch ports, IP address. What do we use here? 6. So it'll be 9 and 10. With a mask. So 9 is there, and that will go to spine 1 ETH1/4. Cool, and then and 14. Perfect. And then the same configuration applies for the rest of the interfaces, or for the rest of the interface configuration, that is. So we'll remove that. Same thing. Three, 2, 4, and there we go. One second, what's happened here? That should have been right. That should be on there, and then int ETH1/3. That should be on there. I think that's correct. 1/3 should go to core. Hang on a sec. Core 1, 1/4. 1/4 has got 5, which maps to 1/3 on spine 2. Yeah, so these should be the other way around. Right, int ETH1/3. 1/4. add that extra configuration. Like so. Get rid of the IP. There we go. Right. So last interfaces we need to configure are the inter or kind of intra-core, should we say? So the interfaces between each core, and then the interfaces between the data centers. So let's look at the core interfaces first. So they are all 1/2. So 10 dot, let's use 99 /30, that's a big subnet. And then same on here, into ETH1/2, no switch port, .2, and then in here, let's do 5. And 6. And again, the same configuration applies for all the other interfaces. So all of this. Wants to go on there. And on the other 2 cores in the other data center. There we go. So now from a DC to DC perspective, so ETH1/1, let's configure those interfaces. So int ETH1/1, no switch ports, IP address, let's use 10.100.101/30, and then the interface that maps to that is DC2 core 1. And we'll configure that as .2, and then DC1 core 2, same thing, but we use 5 and 6. And 6, and then these interfaces have got a little bit less configuration because they don't communicate in OSPF. We don't run OSPF between the data centers. All the DC to DC traffic is handled on the overlay using BGP. So we still want to set the MTU to 92.1.6. We have set the IP address to medium B2B, and we'll now shut the interface. So we'll grab that, get rid of the interface IP, and then whack it on all the other cores. Cool. So let's just do a bit of verification. So show IP OSPF neighbors. We can see that we have got 3 neighbors, which I would expect. So 2 is the other core, and then 5 and 6, if we have a look, are the 2 spines that are local to us. So if we do this on the other core, we should see the same thing. So 1 is the local core, and then 5 and 6 are the local spines. And then over here in DC2, show IP OSPF neighbors, 4 will be the local core, and then 7 and 8 are the local spines. And then on core 2, same thing. So 3 is the local core, and then 7 and 8 are the local spines. So if we have a look on a leaf, so show IP routes, OSPF underlay, we've got a load of routes, and we should see, so from a DC2 perspective, the loopback of DC2 core 1 is .3, so we should be able to, if all is working, ping, there we go, the local core, which shows that we've got connectivity within the data center. We don't, obviously, in here you don't see any of the loopbacks or the link nets for DC1, which is expected because we don't use OSPF over the DCI. So, right, now that's pretty much the underlay configured. Let's just move on to the multicast configuration. So, the multicast for the VXLAN local side of things is configured on the spines as normal. So if we come out of this, we'll say IP PIM RP address. This is the rendezvous point address for this data center, which is 10.0.0.98. We'll set the group list for that to 224.0.0.0/4. And we'll say the PIM source specific multicast range is 232.0.0.0/8, and then we'll say IP PIM anycast RP. So now we want to specify the IPs of the two spines in this data center, which are 5 and 6. So 10.0.0.5. Actually, no. First, we need the RP address, and then we'll go. So like that. So we want the RP address, which is 98 in this data center, and then these are the two rendezvous points. So these are the loopbacks of the local spines. We need to actually create that address as a loopback. So int loopback1, no shutdown. IP address, make that /32. We do want to advertise this in to OSPF as well, because the leaves, the local leaves, will have to get to this address, and we'll also set PIM sparse mode. We do actually as well need to configure PIM sparse mode on the main loopback, and then on the interfaces toward the leaves, so ETH1, 1 and 1, 2. In fact, actually, they'll want to be configured on all the interfaces, so we may as well just do ETH1, 1 to 4. So int ETH, and then IP PIM sparse mode on all interfaces. So let's PIM, let's see if I can grab that. Yeah. So this wants to be the same on DC1 spine 2. So this is the PIM specific configuration. Then again, we want to create loopback 1. No shot that IP address of that. So with it being an anycast PIM address, both spines have that address. There's not a different address for each spine. Underlay, let's get it into area for the backbone, and then IP PIM sparse mode. We'll do that on loopback 0 as well, and then interface ETH1, 1 to 4. Cool. So let's take that configuration and adapt it slightly for DC2. So in DC2 we will be using 99. The source specific multicast ranges can stay the same because they are just the ranges for multicast. It's this address here essentially that's DC specific, and then where we had 5 and 6 in the other data center, we will be 7 and 8. in this data center. These are just the loopbacks of the loopback zeros of the spines. There we go, and we'll do that on spine 2 as well. And then int loop 1 IP address 99/32. No shot that. And then IP PIM sparse mode. Same on spine 2. Cool. And then loopback 0 also on sparse mode. And then ETH 1/1 to 4 also on sparse mode. Cool. So now that we've got that configured on the spines, now we can configure the leaves. So the leaves, the configuration's quite reduced because all we're doing is essentially pointing it at the Anycast RP. So IP PIM RP address. So in DC1 that is 10.0.0.98. Set the group list to exactly the same, so 224.0.0.0.4/4, and then we'll do IP PIM source specific multicast range, and it's the same, so 232.0.0.0/8 if I can type, and again interface loop 0 will say IP PIM sparse mode, and then on the interface it's pointing towards the spines. We also want to do that, so in this case it's 1 to 2 like that. So let's do the same thing. Grab that configuration because it'll be the same on the other leaf in DC1, and then IP PIM sparse mode. Exactly the same on that. But then in DC2, again it's the same configuration, but we are 99 in this data center rather than 98 because we've got a different RP for this DC. 0 IP PIM sparse mode. Cool, and then same on leaf 2. Cool. So, for a bit of verification, we can come onto the spines and do a show IP PIM RP. We can see that this is our RP address and these are the members, so 5 and 6 is correct, and we can see there's an asterisk next to the kind of what we'd call the local RP, because we are .5. You know, if we do a show IP interface brief, we can see that we are .5, and it's a good indicator that that's got the asterisk next to it. Sometimes when you either haven't configured it right or there's something wrong with the underlying connectivity, you won't see this asterisk here. So that's a good sign. So we'll just do that just to prove everything's working on all the spines. So we can see, and you can see the asterisk follows the local member. So again on here, all looks good. In fact, yeah, there you go. So just need to edit this configuration on here because in fact I'll do it based on this one. So it's good that I did that. So we want 99 in this data center, and then I don't know whether will it let me. No, it won't. 5 and 6. But what we actually want is IP PIM Anycast RP 10.0.0.99 and then we are 6 and 7, oh sorry, 7 and 8 in this data center, so 7 and 8. Show IP PIM RP. That's looking better, so you can see we've got the asterisk now, which looks good. So now we want to move on to the NVE configuration, which is the VXLAN VTEP configuration. So for now, that's only applicable to the leaves. It will also go on to the core switches as well, because they'll do a kind of a multi-site flavor of it to get the traffic between the two data centers. So what we'll do on here is let's create loopback 1, and let's do IP address 10.0.1.9/32. No shutdown. IP PIM sparse mode, IP router OSPF underlay backbone area with, don't know what's going on there. There we go. Cool. So let's also configure a loopback 1 on the other leaf, and we'll do .10. Cool. So let's interface NVE1, which is the network virtual endpoint address. We'll no shot that. We will say the host reachability protocol is BGP. We'll say the source interface is loopback 1. Do the same thing on the other leaf, so int NV1. We'll no shut it. We'll set the host reachability protocol to BGP, and we'll set the source interface to loopback 1. Exact same in DC2, so int, what's our local loopback here? Show IP interface brief. Interface loopback 1, IP address 10.0.1.11. All I'm doing is adding a 1 in the second to last octet, so IP router OSPF underlay area 0. And then let's IP PIM sparse mode it. Cool, and then int NVE1. No shot that. We'll set the host reachability protocol to BGP. And then we'll also set the source interface to loopback 1. In fact, in loopback 1 wants a no shot as well. Did I do that on these ones? Let's just make sure for shutdown. Cool, and then last but not least, IP address 10.0.1.12/32. OSPF underlay area for the backbone, and then IP PIM sparse mode, and then the network virtual endpoint. We'll no shot that. We'll set the host reachability protocol to BGP, and the source interface to loopback 1. So what we should be able to do, why have we moved around, there we go, is let's do a show interface NVE1, and we should see that it's up. If there's any configuration that's sort of incorrect or mismatched, the NVE interface won't come up, so that's again a good identifier that the configuration is working as expected. So let's just check that on all the leaves to make sure we are good. You can see everything's up. Perfect. So now we can move on to the multi-site configuration, which is done on the cores. So this is where we start to kind of branch out from the normal, because in theory everything that's been done thus far is sort of normal VXLAN configuration. So you've got your underlay, which we have used OSPF. We've layered PIM on top of that with an RP, a local RP as the spines for Anycast, or using Anycast should I say, and then we've just configured the network virtual endpoint interface, which is the VTEP essentially. That's all sort of standard VXLAN configuration. This stuff now is the specific multi-site configuration, which allows the DC to DC traffic to work. So on the core switches, we need to configure those essentially border gateways to say they are on the border of this data center and give them a number as an identifier. So we do that by saying EVPN multi-site border gateway, and then it wants a multi-site ID. So for DC1 we are multi-site ID 100. You can set a delay restore time, which essentially, if I use context sensitive help, it doesn't give you any additional information, but essentially when the NVE interface comes up, adding this delay will essentially prevent the multi-site loopback from coming up, and it will essentially allow everything internally to converge and connect, and it kind of gives a bit of a safety delay, should we say, to prevent things coming up too quickly and connectivity kind of black hole in for a little bit. So we will configure that. So we'll delay restore time, set it to 100 seconds. Exit out of that. So essentially this configuration wants to be done on both cores in both data centers. And then in DC2 we want to say 200, so we want a different border gateway address, or a different site ID, should we say. And then we will delay restore time 100, and same on here. Cool. So now we need to essentially tag the interfaces as whether they are fabric or DCI for tracking. So for example, if a DCI interface goes down, certain things will happen within the multi-site configuration, and loopbacks may go down and stuff like that. So essentially in our configuration, 2, 3 and 4, or in ETH 2, 3 and 4 are what we consider fabric interfaces, because they are pointing back into the fabric, and then ETH1/1 is the only DCI interface, so that's considered as a DCI interface. So let's configure the DCI interfaces first. So it's essentially set on the interface. So we say EVPN multi-site DCI tracking. So we'll do that on all 4 cores. Just like that. And then all the other interfaces, so interface ETH1, 2 to 4, if we do EVPN multi-site, we get 2 options. So we've got DCI tracking, which we've already set, and then we get fabric tracking, which we need to set for these interfaces. So again, do that on all the cores. 1 to 2 to 4, and then in DC2 cool. So I believe there is a show NVE multi-sites. There we go, DCI links, and then links. So there we can see the interfaces that we've configured as Fabric and as DCI, and we can see the state of them as well, whether they're up or down. So now the multi-site configuration requires an Anycast loopback, which is essentially dedicated to the multi-site configuration. When we look at the routes later on, when they get advertised between the data centers, this is used as a sort of identifier for the routes. So the normal loopback 0 essentially isn't, well, loopback 1 in the case of the leaves isn't used to source the VXLAN traffic. Because it's multi-site traffic, it uses the loopback 100 address that we're about to configure now, which essentially makes it so that the cores are redundant in effect. So we'll configure the same address on both cores in each data center. So there'll be 2 addresses, and that essentially sort of addresses the data center, and any traffic that comes across from the other data center will be destined for that as a VTEP. So yeah, it essentially makes the core switches redundant because they're going to be using the same address. So let's configure interface loop 100 in DC1. We will use IP address 1/32. We will now shut that, and we also need to make sure that it's advertised into OSPF. So show IP router OSPF underlay like that. Cool. So we also want that on the other core switch in DC1. Cool. And then DC2 is similar, but we want 222, 222. And then core 2. Same configuration. Cool. So we now want to set up the NVE interface on the core switches. So interface NVE1. We do still need to do the kind of initial configuration. So no shutdown, host reachability protocol BGP, source interface. We will use loopback 0 for this one, and then we want to set specifically the multi-site border gateway interface, which is loopback 100. So show run interface NVE1. It's essentially the same configuration across all the cores, so we'll just copy and paste that across all the core switches. Cool. That should, if we have a look now, so show interface NVE1, we can see that it's up. And if we also look at loopback 100, this is where it gets a bit weird, because it shows it as administratively down, but admin state is up. And the reason for that is because what's happened at the minute is because we've just configured it. I think if we do a show NVE what the there's essentially a show command that allows you to look at the delay restore timer, and that's what's at the minute is running down. So within, I think we said 100 seconds. I think we said 100 seconds. Did we? Yes, delay restore time 100. So essentially, in 100 seconds, that should go from down, which it looks a bit odd because it says administratively down and then the admin state is up. So we should see that change shortly. But for now, let's begin on the BGP configuration. So let's jump on to the leaves just for a second. So we need to, in fact we can do this globally, it doesn't really make a difference. So let's just make sure everyone's in configuration mode, and then we just need to do an NVE overlay EVPN, which essentially just enables the EVPN configuration parameters for the switches. So let's look at BGP then. So for the overlay, essentially, DC1 is going to be Autonomous System 100, and DC2 is going to be Autonomous System 200. We're going to have kind of normal iBGP connectivity within the local data center, and then between the data centers we'll have eBGP pairings. So it's cleared on me, interesting. Right, so let's start. So route map redist direct permit 10. For some reason on NXOS you have to have a route map to be able to redistribute directly connected routes. So we just need to create one. So route to BGP 100 under the address family of IPv4 unicast. We will redistribute direct with a route map for, let's just copy the name. So essentially what we're doing here is redistributing the loopbacks, so into BGP for the local data centers communication or consumption, and the remote data centers consumption, so that the stuff like the loopback 100 is essentially advertised out. So because there's quite a lot of configuration for the neighbors, we will use templates. So let's do one for spines. We, because this is iBGP, the remote AS is going to be 100. We'll set the update source to loopback 0. So two address families, we'll do L2VPN, EVPN first. We'll send community both, and then we will rewrite the EVPN route target autonomous system number, which is required because essentially we will receive routes from this from these pairings. Essentially, if we're talking about these two core switches here, we're going to receive NLRI, network reachability information, from DC2, and that will have its autonomous system number in the route target, because essentially we're going to use route target auto, which if you aren't aware what that does, the first part of the route target ends up being the autonomous system number, which in DC2 is going to be 200. So as we advertise those out into the local data center, we need to make sure that's rewritten, so that when these spines and other network devices receive that route, it's got the local ASN in it, and it will be put into the right VRF when it lands on those switches. So we need to make sure that we do that, and that's only applicable for the L2VPN, EVPN address family. So we will also enable the IPv4 unicast, and this just needs send community both on it. Cool, so that's all for the spines. Now we want to do a template here for the DC2 core switches. Remote AS is 200, so we're eBGP. We want to set the update source as loopback 0. eBGP multi-hop to 5, because these are going to be, because we're paired on the loopbacks, there will be more than one hop essentially, which eBGP will set the TTL to 1, and obviously that isn't going to work for us. We also need to set the peer type to fabric external, because these are the other data center, so in theory they're external to the fabric. And then again, address family L2VPN, EVPN, send community both. We will also rewrite the EVPN ASN, and then address family IPv4 unicast, send community both. So let's exit out of that. So for the spines in DC1 we are 5 and 6. So neighbor 10.0.0.5 we will say inherits peer spine, and then 6 same thing. So the peerings between data centers go to the cores, and it's the loopbacks on the cores, so that in this case is 3 and 4. So neighbor 3, and we will inherit the peer of DC2 core, and then .4 same thing. And then for the other peering, so there's 2 more peerings that need to be done. So there's an actual physical peering, should we say, on the physical interfaces here, and the same thing between the 2 core switches within the local data center. So let's first do the DCI. So neighbor, what's the address on here, just to make sure I get it correct. Grab that. There we go. Remote AS is 200, and we'll set the update source as ETH1/1, and we'll just enable IP, in fact the address family of IPv4 unicast. Come out of that. And then last but not least, the neighbor, it wants to be the loopback 0 address of the local core. So that's DC1 core 2, which is .2. So neighbor 10.0.0.2, we are IBGP, so remote AS is 100, update source is loopback 0, address family L2VPN, EVPN, send community both, and IPv4 unicast, send community, where's it gone? Send community both. Cool, so that is a lot. Section BGP, that's a lot of BGP configuration. So, because I don't feel like typing it, is that everything? Let's just make sure. Because I don't feel like typing it on every single core switch, let's copy it and come onto here. So we need to replace, in fact, we need to create the route map first. Route map permit 10. Let's create that on all the cores while we remember. Cool. Now let's get the BGP configuration. So we need to make a couple of amendments. So we need to change this to .1 because this is the local core peering. We're now pairing with DC1 core 1, which is .1. They're fine, the local spines are fine, and then this wants to be .6, so that is the local DCI peering. So the DC1 side of that pairing is 5, and the DC2 pairing of DC2 side of that pairing is .6. That's the ETH1/1 pairing. So let's paste that in. There we go. Cool. So now for DC2, the changes will be a little bit more evolved. So we are now in Autonomous System 200. This is going to be DC1 core, which uses an autonomous system number of 100. All the rest of that's fine. The spines, being IBGP in this data center, we'll use AS200. The local IBGP peering between the cores in DC2, we will be peering with .4. So we'll swap that out. The cores in DC1 will be 1 and 2. The local spines in DC2 are 7 and 8. So I'll say 7 and 8. And then the swap that and set that to 1. Let's just check all of that looks good. I think so. Copy that. Paste it in. And then on DC2 Core 2, let's just run through. So we now want to pair with .3, which is our local core. 1 and 2 are the DC2 cores. We probably should change that to DC1 core. And then this wants to be .5. ASN is 200. In fact, no, it is 100 because that is the DC1 ASN, and that looks good. Thinking about that on here, if we just DC1 core, we just need to sort these out. So for a full PGP, for a full PGP configuration, that's what we've got in DC2. So let's do a bit of verification. So show BGP IPv4 unicast summary. You can see that everyone is connected apart from the 2 spines, which we haven't yet configured, which is expected. The same one here, we can see again the only things that aren't connected are the 2 spines, which is expected. And then on here again, 7 and 8 are the spines, and 7 and 8 are the spines. So that is looking good for the moment. So for the spines themselves, let's come on to DC1 spines. So router BGP 100 will enable the address families. So address family IPv4 unicast, and address family L2VPN EVPN. Again, we use templates. So template peer for core. We are remote AS100 because we're using IBGP. The update source is loopback 0. Address family L2VPN EVPN. Send community both. And then the core switches will act as well. Essentially, well, no, the spines will act as route reflectors for the local DC. So we need to set route reflector client on these because we've got, if we look at what we've got here, we've got kind of IBGP stretching over 3 devices, and the kind of rules of BGP are that if I receive a route from an IBGP peer, I'm not going to then advertise it to another IBGP peer. So somewhere in here there needs to be a route reflector, and it makes sense that the spines are that, which is kind of normal for a VXLAN fabric anyway, because if you think about the way the leaves and the spines work, if we lost one of the spines, this leaf would advertise its information to this spine, and then this spine would not ordinarily, if it didn't have the route reflector configuration enabled on it, it would not advertise it to this leaf, because it would not advertise an IBGP learned route to another IBGP neighbor. So That's a critical part of this configuration. So then we will address family IPv4 unicast, and we'll do the same thing, send community both, and root reflector client. Exit on that. Template peer for a leaf. Remote AS 100. We'll set the update source to loopback 0. Address family L2VPN, EVPN, send community both. Root reflector client. Address family address family IPv4 unicast. Send community both. Root reflector client. Cool. So let's now configure the neighbors. So neighbor 10.0.0.1, which is DC1 core 1. We'll set the inherit peer, and that is going to be, where is it, core. .2 is also going to be core, and then the local leaves in DC1 are 9 and 10. So let's do 9, set leaf, and 10, we'll set leaf, and then shall run section BGP. Fortunately, because we've got no kind of local addresses in this configuration, we can just slap that straight onto DC1 spine 2, thankfully. Don't have to root through the configuration and try and take things out and change things. It should just work. So we'll wait for that to apply, and then we should see, whereas before on the 2 core switches, the 2 spine pairings were down, they should come up. Fingers crossed, there we go. And then, so on here previously, these 2 were idle. We'll see one of them is now idle, and should, there we go, come up. Same on core 2. Perfect. They are both now up. So let's copy that and use it in DC2. So 200, 200, 200. The local cores are 3 and 4, and the local leaves are 11 and 12. So whack that in there. Whack that in there. Did that take? Yep. And then DC2 spine 2. Same thing there. And then we should, again, on here, we saw these 2 were idle. They should come up. There we go. And same on core 2. Perfect. So they've all come up. Last but not least for BGP configuration is the leaves. So thankfully it's a bit of a lesser configuration on the leaves, because all we're doing is pairing with the spines. So root BGP 100, address family IPv4 unicast to enable that. Address family L2VPN EVPN to enable that, and then we may as well enable template pair spine. Remote AS is 100. The update source is going to be loopback 0, and then address family L2VPN EVPN. Send community both, and the same for IPv4 unicast. Send community both. Cool. And then the local spines are 10.0.0.5 inherit peer spine and then .6 inherit peer spine. Yeah, so show run section BGP, grab that. That configuration should go onto this leaf as well because it's in the same data center. And then in DC2 we just need to swap the ASN over and also 7 and 8 for the spines, like so. So on the spines themselves, if we did a show BGP IPv4 unicast summary, we can now see that we've got 4 neighborships, which is good, but no one's down. Same on there, no one's down. And then in DC2, again, same there, no one's down. And same on there. I mean, for complete sakeness, you know, you could do a show BGP L2VNI VPN summary as well, but I wouldn't expect any of those to be down either, because you know, if it's down, it's normally due to you know, IP reachability or some sort of issue with the configuration, and if one of them's up, the other one should normally be up. Cool. So that is pretty much it for the BGP configuration. We're all kind of peered. We've got the route reflectors working as we expect. We should actually, if we do a test, so let's have a look. So DC1 Leaf 1, if we do a show BGP IPv4 unicast, we should see, there we go. So now we're seeing the loopback 100 addresses, and these should be able to communicate with these. So bearing in mind we're in DC1, should be able to ping this. In fact, no, we won't, because, and I'll tell you why, on the core, because the remote cores don't have OSPF between them, so we should be able to ping this one. That should work totally fine, which it does, and then from a DC2 perspective, we should be able to ping this. So if we did that, the reason why that doesn't work is obviously we've got the route for it from a DC1 perspective, but if we looked at DC2 core 1 and did a show IP route, we'll see that we still have no. There's a lot there. Let me specifically search for show IP interface brief. So like that. You see there is no, even for loopback 1, there's no route backwards to that leaf, so that the traffic will get to DC2 core 1, but it won't get back. To be fair, we won't ever need to get traffic to that address. It's only ever used locally within the data center to kind of signify that it needs to go to the core switches, and then the core switches will get the traffic between the two data centers. So really, that's not really a problem. Probably a bad address to choose from the from the routing table to test access to. But you can see in here we're getting, you know, lots of good routes coming over. So the last configuration we're going to do in this video is the VNI setup for getting these PCs or servers or whatever to talk to each other between the data centers. So for that, we're going to need to do some configuration on the leaves and the cores, nothing on the spines for the moment. So let's jump onto the leaves in DC1. So VLAN 1000, set the VN segment to 200,000, VLAN 1001, change that, and then interface NVE 1, we'll set the member VNI to that. We will suppress ARP because that's always a good thing. And we'll set the multicast group to 239.0.0.1. Why not? And then we'll do that same thing for the other VNI. And then under the EVPN configuration, we'll set the VNIs. We'll set them as layer 2. We'll set the route distinguisher to auto and the route target for both to auto. And then we'll do the same for the other VNI. RD auto, route target both auto. So let's see, show run section VLAN. Section, oh, in fact, show run interface NVE1, and then section EVPN, because its configuration is the same across all the data centers, or all the leaves, should I say, sorry. So let's just whack the VLANs on all the leaves. And then do the NVE configuration. Take those out because you don't really need them in there. Same on the other two leaves in DC2. And then last but not least, the EVPN configuration. Cool. So we do need to do a similar configuration for the cores. So it's pretty much exactly the same, other than the NVE configuration has got some different stuff in it. So let's add the VLANs to the cores. This is literally just to be able to map the VN segments. The VLANs won't actually be used at a layer 2 level. And then we'll do interface NVE1, member VNI. We'll do this one first. So here we've got to set the multi-site ingress replication, and then the ingress replication protocol is BGP, and then we'll do the same for 1001, and then pretty much the EVPN configuration from the Leaf is the same, so this configuration here. So in fact what we'll do is we'll whack that across all the cores, and then we'll grab the show run NVE1 and we'll grab this specific stuff here. So we'll take that out of there and just whack this on all the cores as well. Cool. So it's essentially the same configuration as the leaves. So here we're creating the VLANs, we're mapping them to the VNID, which is the 24-bit identifier, which kind of gets us out of the cap of 4,000 or whatever VLANs and allows us to have a hell of a load of VXLAN segments, so to speak. Here we're then mapping them to the network virtual encapsulation interface, which is essentially the VTEP. We're suppressing ARP because it's kind of a good thing to do. You may see problems with that if you have like silent hosts or what have you. They'll have to kind of communicate on the network to be able to populate the ARP suppression cache, which we'll look at when we try to do some connectivity between the devices. And then the VPN stuff is pretty much the same. In effect, we're mapping the VNI to a route distinguisher and route targets, and we're setting these as auto. So what we'll see is the auto will be the ASN colon the VNID. So we should see that when we look at the routes shortly. So that should be all the configuration to allow layer 2 connectivity. So at the minute we're only talking layer 2 connectivity, so we're not going to be having, this PC being able to talk to this PC. It's going to be this PC talking to this PC, for example, and across to the other data center. So PC1 talking to PC3, for example. So let's have a look at, in fact, are these interfaces configured 1/3, 1/4 on the leaves? No, they are not. So int eth 1/3 switch port access VLAN 1000 spanning tree port type edge no shut. What we'll do is we'll do the same thing. Essentially, eth 1/3 on all of the leaves is VLAN 1000, and then eth 1/4 is VLAN 1001. So we'll do that, and then we'll change to /4 1001, and then we'll configure that. This is literally, this is literally just for the layer 2 connectivity to the PCs. Cool, wait for that to take. Cool, and same on there. So let's just check show interface status. You can see there that they are connected with the right VLANs. Show interface status, connected with the right VLANs. Oh, int status. There we go. Cool, and last but not least. Cool. So let's just have a quick look. The machine shouldn't have communicated, and we can check by doing a show MAC address table interface 1/3, and we can see that we can't see a MAC address there at the minute. And if we do a show IP ARP suppression cache for VLAN 1000, we'll see there is nothing in there. Let's just actually set the terminal width everywhere. Cool, so we get things nicely laid out. Cool. So I'm pretty sure with these PCs, when you set the IP, it essentially will ARP because it's checking for a duplicate address. So let's see if... So now we've got a MAC address, and then if we look at the ARP suppression cache, we can see that we've got a local layer 2 entry, essentially. So if we check, before we try and communicate, if we check this elsewhere, essentially we'll see this, which is a good sign, which shows that things are possibly working, which is good. Essentially we've got a remote entry in here, which we can see by there, and we can see the remote VTEP address, and that is the address essentially of DC1 Leaf 1. That's its loopback 1 address. Hopefully, if we look in the other data center, we can see something similar. Instead, though, this time, and this is where I was saying that the multi-site loopback, which is loopback 100, essentially is used to get traffic out of the data center into into the other. So essentially here, instead of seeing the loopback of like we're seeing on here, where we see the actual physical loopback of the of Leaf 1 in DC1, we see the core multi-site address in DC2, which we can communicate with. We can't communicate with the loopback 100 in DC1 from DC2, but we can communicate with the loopback in DC2. We should then also see that on here as well, which is a good sign. And then because that's all working, I'm pretty happy that what we should be able to do is, and just to show you how this ARP suppression stuff works, so if I come on here and go 10.10.1.11, for example, we can see that's working. That's the local data center. So now if we looked at Leaf 1 and do that again, we can now see a local entry, and we can see a remote entry. So this is PC1, this is PC2, and we can see that it's got the remote VTEP address of DC2 Leaf 2, and we can see that that communication is working because we can ping between. Now to take that one step further, let's try and ping this. So this is pinging between the two data centers, and we can see that that's not yet reachable. So what we may have to do is on this PC, if we just look at the ARP suppression cache, we can see that we don't yet see an entry for that. What we may have to do is we may have to just trigger something to ARP, and if we come back, we'll see that now we've got an entry for it. So that's kind of the ARP suppression stuff coming into play. We should now be able to do that ping, and it should work just fine. If the host doesn't communicate on the network, it won't populate this suppression cache, and if it doesn't populate the suppression cache, the whole point of ARP suppression is that we don't flood them across the network, and it won't reach DC2, and that it will never reply to the ARP and populate it because it won't get it, because we are suppressing the ARP. So it's just one thing to bear in mind when you do enable ARP suppression, that you need to either not enable it if you've got silent hosts, or enable it, but keep in mind that you may need to get those hosts to communicate somehow before they can be communicated with. So from a VLAN 1000 perspective, we can prove now that we've got DC to DC communication. So this PC1 is in DC1, this PC3 is in DC2. We should be able to ping 10.10.1.10, so ping back from DC2 to DC1, which we can, which is good. And then just for completeness sake, let's have a look at the other VLAN. So let's just redo this to get these communicating on the network, to get them to at least populate the ARP suppression cache. There we go. So we should be able to ping 11, which we can. We should be able to ping 12, which we can. We should be able to ping 13, which we can. So we've got essentially, full layer 2 connectivity. Obviously, layer 3 connectivity isn't going to work. If I tried to do that, which is essentially pinging this PC here in VLAN 1000, that isn't going to work because we don't yet have routing set up with any CAS gateways and all that kind of jazz. So from a layer 2 perspective, that's working. If we wanted to look at the actual routes themselves, so exit. So let's check a local route on here. So show BGP, L2VPN, EVPN, and let's check .10, which is our local PC in VLAN 1000 essentially. We will see in here that it's a type 2 EVPN route, which means that it is just the MAC address. Type 5 is, well, I say just the MAC address. It's the MAC address and a /32 IPv4 address. Type 5 is where we start looking at like subnets and stuff. So when we're talking about advertising subnets in from these firewalls, they'll come in as type 5 routes, which is just an IP subnet. There's no MAC addresses attached to that. So we can see here that that is the MAC address for this host, which it is, and that's its IP address, which it is. We can see from here it's a /32, and we can see that we have locally originated this, which makes sense because it's local to us. And this is where we look at this extended community, so we can see that the autonomous system number being 100 in DC1 is sat there, and then the VNI is there, and that's what I was saying with the root target of auto. That's what it essentially does. If we go one step up and look on the spines in DC1, we can see here again the same thing. It's the type 2 route that's come from this leaf. We can see that that's where it's come from, so that is 10019 is DC1 Leaf 1's VTEP address, and it's it's got the same information essentially attached to it. If we looked at this from the other data center, so essentially remotely from Leaf 1's perspective in the other data center, we can see a lot more information. So again, it's the same type 2 route as here, so we'll just focus on this top one for the moment, but it's the same type 2 route, it's got the same MAC address, it's got the same IP address. We can see that we've got two paths to it. It's got the same kind of address, should we say, but the actual where it's originated from is the two spines in DC2, so .7 and .8, and the reason that this one has been selected is neighbor address. It's got down to the very last BGP path selection attribute, which is neighbor address, and that's why this one is best. And again, we can see that this is where that root target swap stuff, or the rewrite, comes in on the core switches. So it swaps out the 100 version of this in DC1, which we can see on here. So we can see there it's 100, 200, 1000, and then here it's 200, 200, 1000, which essentially needs to be done because the root distinguisher is that in this data center, and it needs to come into the right place essentially. If it doesn't, then it wouldn't be here, and you wouldn't have connectivity. So that's why that's really critical. We can see as well, because we've got the cluster list stuff in here, that it's come from a root reflector. You wouldn't see that if it was just kind of a normal, BGP sharing of a root. You wouldn't see the cluster list in there or the originator. So that's good to see. And then essentially, everything else is the same on the other routes. We can see the same information, and that's how everything's shared between the data centers. If we looked the opposite way, just to really kind of look into it, if we looked at show L2VP or show BGP, L2VPN, EVPN for, let's do 10.20.1.10, we can see the same thing. It's just a route from the other. In fact, no, we're in DC1, so let's do 13. Yeah, there we go. That's more like it. Again, we can see that it's coming from the local signifier of our data center, which will get it over to the other data center. And again, the root target's been rewritten as it's come across, because in DC2 this will be 200, 200, 1001, and it's been rewritten to 100, 200, 1001, which makes sense. So that's essentially it for this video for the layer 2 connectivity. In the next video we'll start to add anycast gateways and the tenant configuration, and get the PCs from the different VLANs communicating with each other, and then probably do what we did with the other set of videos for the VXLAN stuff, and split them out into different tenants and show how the root leaking works from a border leaf, should we say, standpoint, which we're going to be using anyway because we've got these firewalls down here. So leaf 2 and leaf 1 over here will be our quote-unquote border leaves. So that will be coming in a future video. But for now, thank you for watching, and hope to see you in the next video.